Welcome back, everybody. AP Chemistry. We're in Unit 5. This is Section 3. We've been looking at voltaic cells in this unit, and with the next part of all of this is taking a look at voltaic cells, figuring out how much energy is going to be involved, is the reaction going to go, all those types of things. And this is also a section that's going to introduce three variables that are going to be basically used throughout the rest of the year. And so let's take a look at those three variables. One is taking a look with the spontaneity, and this is going to be our potential of energy. That's a measure of the spontaneity of a cell reaction. Okay, so that's of the electrochemical cells and so on. But the other two variables that are going to be a theme throughout the rest of the year is taking a look at the equilibrium constant. Equilibrium constant is a K constant, and then we have something called Gibbs free energy. Okay, so couple of things before we get going with how this applies specifically to this chapter. But first of all, let's just go down the line. We called this Gibbs free energy, and we see that if I have a negative value on this, that will be a spontaneous, I should say, equation. And so with that, basically all we need to know at this point, if it is negative, that type of reaction will end up being exothermic. Okay, and again, this is going to be a theme that comes up throughout the rest of the basically the rest of the year. So don't worry about it at this point too much. Just get into your mind some of these kind of concepts. So we also have a K value. This is going to be the calculated equilibrium constant, and it tells us that a K value that is greater than 1 is deemed spontaneous. In other words, the reaction will go on its own without need of some kind of accelerant of some type or some type of catalyst. Now, by this, we're going to be finding some values. Anything larger than 1 would be deemed a large value of K. And the reason I say that right now is because you're going to get some numbers of K that's going to be something like 10 to the negative 6. So that would be non-spontaneous, and we'll see what to do with all of those types of things. And then lastly, we have what we've had throughout this entire chapter so far is dealing with the potential energy amounts. So we'll take a look at those values by using our redox charts that go with this. Okay, so it's a potential energy that's going to be available to deem the spontaneity of a cell reaction. Okay, so how all of these things are related, all three of these variables will be calculated out. And so we can see, first of all, let's take a look at a relationship between my Gibbs free energy and the potential energy that's in here. So here's your equation that you'll need to know that Gibbs free energy, the change in this energy is a function of the negative of n. Now the n is my number of electrons that are involved in the reaction. Careful, sometimes n stands for the number of moles. In this case, it's the number of electrons that are involved. And that's times something called Faraday's constant. Faraday's constant is something that's going to be provided on your AP charts. And so with sorry about not being able to spell constant, but Faraday's constant will be provided for us on our charts. Just know that Faraday's constant is going to be listed as 96,480, and that will be the units is what's important. That's going to be in joules over moles times my voltage in this case. A lot of times we're going to be using instead 96.48. That will be in kilojoules per moles times my voltage. Okay, so just be aware that on the AP exam, this number is going to be provided, but those units are going to be in joules. So you can see that this is going to be Gibbs free energy is the number of the negative times the Gibbs free energy times Faraday's constant times my potential of energy here. Now, how this ties then with my spontaneity based off of the equilibrium constant, my potential energy here is going to be a function of 0.0257 times my n, which is again the number of electrons, times the natural log of K, of that equilibrium constant. Okay, so it's just taking a look at those two equations. These are just plug and chug at this point. You just put the numbers in and solve. But notice that my K will be related to my E, and then I can take that E and solve for my G. So you're going to be bouncing between these equations a little bit to find those. So you do have to have mastered the different applications as we go. All right, so let's take a look at this type of reaction, and let's find those values of my Gibbs free energy and my equilibrium constant. So for this, I will need to, first of all, balance my I will need to balance my redox reaction. And so I'm just going to go fast through this. Notice that my silver, and it's important to see which one's going to be oxidized and which one's going to be reduced, because we've got to be using our chart, and this chart is the standard reduction potential. So we've got to figure out who's being reduced, who's being oxidized. So that's a -2. This is going to be a +5 then. This is going to be a +1, -2, +2, -2, +1. All right, so we take a look at this, and I see that my reduction agent, okay, the thing getting reduced in this case would end up being my nitrogen, because my nitrogen is going from a 5 down to a 2, so it's getting reduced, it's gaining electrons. So let me balance this out. This is an easy one to balance on your own. You've got to be able to balance the redox reactions, and we end up with nitrogen monoxide plus 2 waters. Now, if I take a look at my chart up here, I see my nitrate and I see a 0.96 value. I'm going to actually go a little bit deeper into that just for the sake of accuracy. We're going to go down and I'll use a different number. That's going to be a 0.964 volts. Okay, so that's no big deal. You can use your 0.96, you're good. Now, the thing that's going to be oxidized then, okay, that will be my silver, because it's going from a 0 to a +1. It's losing electrons. And so if I was going to balance this out, I would end up needing 3 silvers. That's going to be my solid. And that will give me 3 silver ions and 3 electrons. And then my oxidation value, if I take a look at that, my oxidation value of my silver, well, this is the reduction value, 0.80. But since it's not being reduced, it's being oxidized, I need to use the negative of that. Keep that in mind, the oxidation value. And again, I'm going to go a little bit deeper than that. I'm going to go a 0.7995. Yes, your chart will use 0.80. That's fine. I don't have a problem with that. So what's the change? What's the difference in this of what's the potential of the energy? I subtract those two and I end up with a 0.165 volts. Okay, so that's going to be my energy potential. Okay, so now I've got all the pieces. Notice that this is a positive value. Okay, and so as we go, let's go ahead and find our delta G. My G value is going to be a function of the negative of the number of electrons times my Faradays times that E value. So again, like I said, you just plug the numbers in. Okay, so my delta G is going to be a negative. I had 3 electrons. 3 electrons are being used here. I saw that my Gibbs free energy, I'm going to use the kilojoules in this case. And so we're going to go 96.48. And then I found my E value was a 0.165. And again, that's a positive value. So if I do this, I end up with a value of my G value is going to end up being a negative 47.76 kilojoules. Okay. Now the question is, okay, if it is a negative V, it is spontaneous there. So I can provide this information of my delta G. Okay, now let's take a look at how my K value comes into this. My K value, again, is a function of my potential of energy, and that's going to be 0.0257 over my number of electrons times the natural log of K. And I want to find K. That's what I'm looking for here. So let's plug our values in. We saw that we had a 0.165 volts. That equals 0.0257 divided by 3 times the natural log of K. Okay, let's multiply both sides by 3 to get it out of there. And so then I find that I have a let's see, that ends up being a 0.495. That will equal 0.0257 times the natural log of K. So if I do this, I find that I end up with 19.3 equals the natural log of K. And so the question is, how do I get K by itself? Well, I take the inverse. Basically, I'm dividing by the natural log, which is multiplying by the inverse. The inverse of the natural log of K of this 19.3 ends up being a 2.3 times 10 to the 8th. Okay, so my K value ends up being that which is definitely larger than 1, and once again, that is going to be deemed spontaneous. So you see, it's just plug and chug. Don't stress out as long as you know the equations. We just take our values and keep track of what are we solving for. So let's do one more of these, taking a look at the manganese. Now, this is kind of a weird one because as I take a look at this, my manganese is a +2. Here's a -2, +1, -2, so this means a +4. Oop, and let's see, and then I have a +1 here. All right, on this side, I have a -2, and so this ends up being a +5. Okay, so in one case, I see my manganese is going from a +2 to a +4. Okay, it's losing electrons. But in this case, it's gaining electrons. So manganese is both oxidized and it's reduced. Let's take a look at the reduction value. Okay, the reduction value, if I was going to balance this out, this ends up being a fun one, by the way. Balancing out your equation, you're lucky I'm just doing this one for you. And I'm going to end up with this. That will give me my Mn2 plus 4 waters. Now, if I look back on my chart, if my manganese is being reduced, I would end up having a 1.512 volts. Okay, now let's take a look on the oxidation end. Okay, and again, you're going to be given these values for the reduction potentials and everything, so be able to read your charts. So I have manganese ion, and in this case, it's being oxidized into my manganese oxide, and I get 4 hydrogen ions and 2 electrons in here. And then if I use my table, now be careful, this is the case where manganese is being oxidized. So I end up with a negative 0.1229 volts. So I see that this is going to be, my potential is going to end up being just barely there, 0.283 volts. This is going to be spontaneous because it's positive. All right, so now from there, let's find my delta G. Okay, so my delta G is going to be a negative of my N times my F times my E. Okay, so let's find that, my delta G. And remember, we had 10 electrons involved in this. So it's a negative of 10 electrons times my 96.48 of Faraday's constant. And I had a 0.283 volts. And so I end up with a delta G of negative 273 kilojoules. Is it spontaneous? You bet, because it's a negative delta G value. Okay, now let's find my K value. Okay, so let's find K. To find K, I take my E value, and I take 0.0287 volts divided by my number of my electrons in there times the natural log of K. So let's substitute values in. I see that I have 0.283 for volts. That's my E value, and that's going to be equal to 0.0287 over 10 electrons involved, and times the natural log of K. I end up with 110.1 equals the natural log of K, and how I got that was I multiplied both sides by 10, and then I divided by 0.287. Okay, so that's how I got my 110.1 times the natural log of K. Again, how I do this is I take the inverse of K. So I do the inverse of 110.1. I end up with a K value of 6.6 times 10 to the 47. That is definitely a large value of K. So we see pretty straightforward how to solve for those types of things and be able to solve those. Now, I'm just going to throw this out here for your reference. There are 3 things. I've been mentioning this along the way that cause making something spontaneous. Okay, so there's 3 things. Take a look at your voltage. Okay, your voltage is going to be that E value. Take a look for that. That should be a positive voltage. Take a look also at your delta G. That should be a negative value. Okay, that's your free energy in there. That's the heat or work done on the system. Take a look also at your K value. That should be a large. Okay, an example of that, if we suppose, let's just take a look at some of these things, how you can calculate your K in another way. And this is just kind of a flash forward into spontaneity. Let's take a look at an example of just figuring out K from an example. Okay, so let's suppose that we have an equation, just something like A plus B divided by C. How you know this is going to work? Okay, finding K, finding that spontaneity, here's how you do this. K will be a measurement of the concentration of the products. Okay, you multiply all the products. So if this is like times D or whatever, we do that. Now, what I do is I take a look at my coefficients in front. If I have a 1 in front, then I have a 1 in front of here. If this ended up being 2, I would need 2, and so on. But in this case, we just had a 1 in there. Okay? Then my spontaneity is going to be a measurement of my products over the concentration of my reactants. And once again, if this is 2, if this is 3 or whatever, I would square it or cube it or whatever. But that's all we're doing. If I see that the multiplying all these things across in my products, if I find that value is larger, and then divide by all my reactants, if it's larger, then it will go. If I find that my K value ends up being really small, a lot of reactant is being made, and it probably won't go in those respects. Okay, so that's just a preview into my spontaneity, and that will come up in another chapter, and that's actually 2 units from now. We're going to be taking a look at those components. Okay, so you've got everything you need to do for this type of reaction, and with that, make sure you know your equations, make sure you know how to do your table, and for heaven's sakes, you should know how to balance a redox reaction by now. But this is pretty easy. That will get us into problems 1 through 4. All right, good luck.